Hi, my name is Anne Marie Bigarello, and today I'm going to be talking about the most dangerous types of acids. Alright, so first I'm going to begin with aqua regina, which is a combination of HNO3 nitric acid and HCl hydrochloric acid. And this can dissolve noble metals such as gold and platinum. Alright, some of the dangers. Aqua regina combines the chemical burn dangers of two highly corrosive, strong acids. The mixing of these acids to make aqua regina releases toxic vaporous chlorine and nitrosyl chloride. Nitrosyl chloride decomposes into chlorine and nitric oxide, which reacts with air to form nitrogen dioxide. Reacting aqua regina with metal releases more poisonous vapors into the air. Alright, and as you can see here, this is an image of aqua regina. It is an orange solution, and dipped in it is a piece of gold, and the bubbles indicate formation of a gas, and in this case it would be a poisonous gas into the atmosphere. So a lot of the dangers associated with this metal occur when something is vaporized and released into the atmosphere. In this case, it is poisonous. Alright, so next I'm going to be talking about Carros acid, which is also known as Purina solution. Alright, so this mixture of sulfuric acid and hydrogen peroxide devours almost any organic molecule it encounters. Today, this acid finds its main use in electronics industry. In the past, it was used in chemistry labs to clean glassware. However, today, it is unlikely you will find it in a chem lab because even chemists think it's too dangerous. Alright, so some of the dangers. In preparation, when sulfuric acid and peroxide are mixed, it creates heat, potentially boiling the solution and tossing bits of hot acid around the container. This exothermic reaction could break the glassware and spill hot acid. An explosion may occur if the ratio of chemicals is off or if they're mixed too quickly. Once mixed, the presence of too much organic matter may lead to violent bubbling, the release of explosive gas, and destruction. When disposing of it, you can't react it with a base, which is normally how you would neutralize most acids before disposing of them. And this is because the reaction is vigorous and releases oxygen gas, which could potentially cause another explosion. So it even poses risk when trying to dispose of it. Alright, and here is the Purina solution, or Carros acid. And as you can see, it's a colorless acid, and here it looks to be dissolving a metal substance. Alright, next I'm going to be talking about hydrofluoric acid, HF. Hydrofluoric acid is a weak acid, meaning it doesn't fully dissociate into its ions in solution. This acid is used to make fluorine-containing drugs and also has several practical lab and industrial uses. Alright, HF eats through just about anything, including glass, so it's stored in plastic containers. Inhaling or ingesting even a small amount of hydrofluoric acid is usually lethal. If you spill it on your skin, it attacks your nerves. This causes loss of feeling, so you might not know you've been burned until a day or more after exposure. In other cases, you'll feel excruciating pain, but you won't be able to see any visual evidence until days after exposure. If the acid enters the bloodstream and reacts with bones, the fluorine can bind to calcium. If enough gets into your bloodstream, the disruption of calcium metabolism can stop your heart. If you don't die, you can suffer permanent nerve damage from this, including bone loss and persistent pain. So it's this is a very destructive acid, especially when humans are dealing with it, because it can be very, very harmful to our bodies. Alright, and here's an image of HF, and as you can see, it is a clear substance. Alright, so next I'm going to be talking about fluoroanatomic acid. Alright, so this is also thought to be the worst acid to man, and many consider this to be the strongest superacid. Like all acids, fluoroantimonic acid is a proton donor, which means it increases the concentration of H+ ions when added to water. Fluoroantimonic acid is able to donate protons, exponentially more efficient than pure sulfuric acid. Right, so some of the dangers: if fluoroantimonic acid encounters water, it reacts vigorously. If you heat it, it decomposes and releases toxic fluorine gas. This acid, however, can be held in plastic, so it is containable. If you were to pour fluoroantimonic acid over your hand, expect it to eat through your hand into your bones, and the rest you probably wouldn't see because either the haze of pain or cloud of vapor rising up as the acid violently reacts with water in your cells. So that being said, this is not a commonly used acid as it is way too dangerous to be in most settings. Alright, so this is an image here of it being poured over what looks like to be a spongy substance, and as you can see, it is instantly burning it. Alright, so on the next slide, I'm going to show images of what acid burns look like and some of the destructions they could cause, so if you don't want to see, I would skip over this part of the video. Alright, so as you can see here, that oftentimes it causes deformities because this will continue to melt your skin, and it stays on your skin and can even be like corrosive to certain parts of your skin. Sometimes it causes loss of feeling while it's doing this, and even sometimes an ashy substance can appear on your skin, and this is because once it's on your skin, it can be hard to get off, so it causes often inconsistencies. They look a little bit different than regular burns. Alright, so I'm going to be talking about Jessica Ray, and her relation to this topic is that she focuses a lot on proper disposal of certain materials and how to clean up hazardous materials when they get into our waterways, and this is why we neutralize any acids or bases before we dispose of them so they're not harmful to the environment. Alright, so she started her postdoctoral studies at the University of California, Berkeley. It was 2015 and the state was in its fourth year of what would be a 7-year drought. There's also rising evidence that there will become more droughts in this region as there will be places around the world. This helped her focus on her scientific mission, and she wants to use her expertise in surface chemistry, material science, biogeochemistry to engineer a more effective way to treat water. Alright, so I'm going to be talking about some of her work. She developed a sand-like composite coated with polymers that target carbon fluorine, PFAs, backbone. The PFAs can then be selectively desorbed from the treatment medium, allowing Ray's team to concentrate the pollutant in order to more effectively break it down. The usual PFAS reduction method requires precise conditions such as the absence of oxygen or high pH. Ray is working on a simpler method for breaking down concentrated PFAS, and this is based on a relatively young class of 2D electronic materials, which have been explored for the use in energy storage. Their fast charge kinetics and high surface area also make them promising electrocatalysts for oxidizing PFAS. And PFAS also include dangerous acids, so it could clean what would cause a dangerous pH in the water. It could help clean our waterways. And you could see an image over here to the side. So that is my extra topic. Hope you liked the video.